All right, L'Hopital's rule. All right, this guy right here with the cool shades, you know he's cool because he has shades, is his French name, his French guy's name is Guillaume de L'Hopital. All right, the book says he was a competent mathematician, so maybe not the best mathematician, but he did come up with this rule and was the first to publish it. And his teacher was a guy named Johann Bernoulli, which is a really, really great mathematician as well. And he was friends with a whole bunch of good mathematicians around his time. Okay, so this is one of those guys, he's not the valedictorian of his class, but he's friends with all the smart kids. All right, but he did come up with this rule. All right, his rule talks about when we're evaluating limits. Okay, I know that's a bad word, limits. All right, but sometimes when you're evaluating limits, all right, you can plug in the top and you get a number, plug in the bottom, you get undefined, and you could find an answer. Okay, or you can just plug it in. Right? Other times, though, you get something called an indeterminate form. And that's when we have 0 divided by 0 or infinity divided by infinity. Okay, in fact, if you haven't already, you can ask Siri what 0 divided by 0 is, and she'll tell you something about you don't have any friends and Cookie Monster is sad as well. It doesn't make sense. Okay, these are called indeterminate forms because I'm not exactly what they are. What they are. 0 divided by 0 is not really undefined. It's indeterminate. Could mean there's something else going on. Same thing with infinity divided by infinity. Which infinity is bigger? I don't know. We could do some analysis to figure out. But with L'Hopital's rule, what Guillaume found out is that if you have an indeterminate form, which is important that it's indeterminate, you can actually just take the derivative of the top, derivative of the bottom, and do the limit again. And if you find that limit, it's the same as the original limit. It works every time if you have an indeterminate form. All right, so let's take a couple of seconds to look at some easy examples. All right, example number 1. Limit as x approaches 1 of x squared minus 1 over x minus 1. First thing you need to do is make sure that it is, in fact, indeterminate. So if you plug a 1 in, you get 1 minus 1 up top, which is 0, and the bottom 1 minus 1, which is 0 again. Okay? So this is indeterminate. Doesn't mean the limit's indeterminate, just means that the form as it is indeterminate. Okay? We could go through and we could factor some stuff out, which is what we did on the first test, and it's really not that bad. Or you can use L'Hopital's rule. L'Hopital's rule says that if that is indeterminate, we can set up our limit again as x goes to 1, and then just take the derivative of the top over the derivative of the bottom. Okay, no quotient rule here, just taking the derivative of the top. Derivative of the top turns out to be 2x minus 0. The bottom, the derivative ends up just being 1. And now, can we plug in? Yes, we say 2 times 1, which is 2, divided by 1, so our limit is 2. All right, same thing here. If you plug a 1 in, 1 minus 1 on top is 0. 1 squared minus 1 on bottom is also 0. Again, you could factor out x squared minus 1, cross some stuff out and do it. Or use L'Hopital's rule and say the limit as x approaches 1 of the derivative of the top, which in this case is 1, over the derivative of the bottom using a power rule, it's 2x. Now I can plug in and get 1 over 2, or 1/2. All right, same thing on this last one here. If I plug a 1 in up top, 1 minus 1 is 0. The bottom, a little more complicated, not much. You get 1 minus 2, which is negative 1, and negative 1 plus 1 is, in fact, 0 again. So it's indeterminate. So I can do L'Hopital's rule and say this is the limit as x approaches 1. Derivative of the top is 1. Derivative of the bottom is what? 2x minus 2. All right, in this case, we say, hey, I can plug a 1 in, but I'm still, what, 0 on the bottom? But that no longer is indeterminate. 1 divided by 0 is simply just undefined. Okay? The limit does not exist. Okay? We can maybe do some other analysis of it and figure out whether it's infinity or negative infinity from one way or the other. But overall, the limit does not exist. All right. Do a few more examples. Maybe some more complicated limits. All right, so I want to evaluate this limit as x approaches 0 with some trig functions going on. Again, we need to make sure we know what the trig functions are at certain values. So we plug a 0 in, we get 1 minus the cosine of 0 over the sine of 0. Cosine of 0 is 1, so we get 1 minus 1. Sine of 0 is 0, so we do in fact get 0 divided by 0. It's not indeterminate. L'Hopital's rule does not apply. In this case, it is. So we can use L'Hopital's rule. Limit as x approaches 0. Take the derivative of the top. Derivative of 1 is 0, it goes away. So we've got a minus. Derivative of cosine is a negative sign. And then the derivative of sine is cosine. All right, clean that up a little bit. This is the limit as x approaches 0 of the sine of x over the cosine of x. Plug 0 in. The sine of 0 over the cosine of 0. Sine of 0 is 0, cosine of 0 is 1, and so we do get the limit of this thing is 0. L'Hopital's rule comes in handy. All right, let's look at this one. All right, this is an indeterminate form, infinity over infinity. You plug an infinity in. E to the infinite power is equal to some infinite number. Over infinity, well, that's also infinity. Which one is bigger? All right, we had that discussion. Okay, L'Hopital's rule makes it infinitely, see that pun there, easier, infinitely easier. All right, since it is indeterminate, we can use L'Hopital's rule. All right, what is the derivative of e to the x? Well, that's boring, it's e to the x. All right, but what's the derivative of x? It's 1. So now if we plug in, we just get e to the infinity minus 1, which is infinite. Okay, we no longer have infinity over infinity, so which one wins out? We see that which one wins out? The e does, because the x just goes down to 1 when we take its derivative. Easy. All right, let's do this one. We got an x squared up top and the e on the bottom. All right, plug infinity in. Infinity squared is infinity. On the bottom, e to the infinity power is also infinity. So it's indeterminate. We do L'Hopital's rule once. All right, the top turns into 2x. The bottom is still e to the x. We plug in again. 2 times infinity, well, I'm still infinity. On the bottom, e to the infinity power is still infinity, so I still am indeterminate. Well, guess what? We can use L'Hopital's rule again. All right, and so what is the derivative of the top? Derivative of 2x is just 2. Derivative of e to the x is still e to the x. So now if you plug in, you get 2 over e to the infinity power, which is infinity, and 2 over a really large number is 0. Not too bad. We just have to use L'Hopital's rule twice. All right. I changed up example 2, 3 to make it a little bit harder on us. All right, we got limit as x approaches infinity of x to the 99th power over e to the x. Infinity to the 99th power is really large. E to the infinity, still large. So, L'Hopital's rule. All right, the top turns into 99 times x to the 98th power over e to the x power. I'll plug infinity in. I still have infinity over infinity. Okay? And the top looks really, really big because I got 99s and 98s. And in fact, for a long time, if you're plugging in random numbers for x, for a long time, the top does win out. Okay? For the longest time. All right, but then we can do what? Indeterminate form, I can do L'Hopital's rule again. L'Hopital's rule again. All right, this turns into 98 times 99, x to the 97th, over e to the x. Because the derivative of e to the x is just e to the x. Well, I'm still indeterminate. Well, I could do L'Hopital's rule yet again. All right, and it turns out I can do L'Hopital's rule like 98, 99, 100 times. All right, but eventually you're going to get the limit as x goes to infinity. Well, these each would come down in succession, so at some point I would get 99 factorial x to the first power, because I brought 99, 98, 97 down, all over to the e to the x, which is still indeterminate. If I take it one more time, I get just 99 factorial because the x goes away. All right. And even though 99 factorial is really, really large, it's not infinity. e to the infinity is infinity, so a really large number divided by an even larger number is essentially 0. In fact, if we do it one more time, apply L'Hopital's rule one more time, which actually we cannot, because it's not indeterminate anymore. But we can think about it, that's almost really, really big, right? What's the derivative of that really, really big number? It's 0. But eventually we do, however you think about it, infinity wins out, e to the x wins out, we get 0. Okay, so then maybe that's a better explanation than what I did previously in class to decide, hey, which one wins out. All right, let's go to our next real example here. All right, let's find this mistake. All right, they've applied L'Hopital's rule in the string of equalities, and where do they make their mistake? Because this is not true. All right, so if I plug a 0 in, 0 squared is 0. We're good there. E to the 0 power is 1. 1 minus 1 is 0. We're indeterminate there. All right, did they do the L'Hopital's rule correct? X squared goes to 2x. That's correct. E to the x goes to e to the x. The 1 goes away. We're good there. We plug a 0 in. We do end up getting 0 over e to the 0 power. All right, but what's e to the 0 power? It's 1, isn't it? Okay? E to the 0 power is equal to 1. This is no longer indeterminate, so this stuff doesn't work anymore. This is just 0 over 1, which is 0. Okay? It has to be indeterminate. You can't just do it until one of them goes away. Okay? You got to continue to do it. You can only continue to do it if it's indeterminate. By plugging in 0 here, it's no longer indeterminate. It is just what it is. All right, and the next 2 pages are your homework. So we are done with L'Hopital's rule. Take a look at those. So good luck. I'll see most of you on Friday.